Good morning. Good morning, everyone. Just like to make a short announcement. Well, no, it's not really an announcement. Just a reminder. So those of you who want to have the mentoring session, you should go to the summer school webpage, the PhD Symposium. You click there, and then you can contact one of the organizers of the FDA Symposium. Okay? If you look at the program on Wednesday afternoon, you have a slot at the end of the day to have these mentoring sessions. Okay? So, welcome again. So this morning we're going to have the lecture on user models and interactive IR. So the lecture will be taught by Romain and Martin. So both Martin and Romain from the University of Amsterdam. Romain is doing a PhD with Martin, and Martin is the head of one of the reference groups in Europe nowadays in IR. So it's a great pleasure to have you both here for this lecture this morning. So thank you very much.
All right, thanks for having us, and good to see all of you. So let's see if we can get this to work. This is us, Romain and myself, and what we've done is we've prepared some slides where we think you'll find some good starting points for thinking about learning from interactions with users. So the title maybe of this lecture is a bit ambiguous. It's not about user studies. It's about data that arises from interactions between users and systems, and learning from this data either to evaluate the system or to optimize it. So we'll get you going on this.
Maybe just one comment. There are a lot of references in the slides, and usually it's not the original paper. It's some kind of resource that we think is a good starting point. So, if you are interested in a specific topic, you just put in the slide, click the link, and get started.
Yeah. So these are, we think, some good starting points. Is a book on user models or click models. Papers that are good starting points because they bring a few threads in the literature together. A tutorial also that is super helpful. It's overlaps somewhat with ours, but it has lots of other angles as well. Now, so we have two objectives, and hope that you will get at least this outcome. So we'd like to get some of these basic concepts and fundamental methods of learning from interactions across to you, and we hope that you'll be able to begin to implement, experiment with them, at least the basic counterfactual learning terrain methods and maybe some bandit methods, get some libraries and start playing with them. The slides are here. That's a more recent version than what's on the summer school site. We'll share the latest version with you later today. We'll also add the references. I don't think we put them up there yet. We'll do that a bit later today. So, can I take this away? Okay. All right. So here's our schedule. I'll give a bit of background, set the scene. I'll share some details around counterfactual learning to rank, and then Omar will take over, talk fairly extensively about bandits, about reinforcement learning and information retrieval, and then we'll get back together again, see what we've actually done. There's some time towards the end for Q&A, but also along the way there are quite a few stops where Any questions that may come up, any suggestions that may come up can be shared. But if you have an urgent question, don't wait for these for this moment. Just want to say shout, or maybe slightly more polite version of shouting. All right, so let's set the scene. In this part, what's it going to be about? Well, it's working from this assumption, from this perspective on information retrieval as systems that work with people to get those people the information that they need. So this could be answers, documents, it could be with a query, it could be without a query. In these interactions, data is collected during these interactions. From this sort of data, we want to be able to learn. So we're going to share some core concepts around this, learning from it, evaluation using it, and we'll make a few distinctions: online, offline, on policy, off policy. So here's a very lonely world of a user. Let's see. Where should I stand? This way I'm not blocking anyone's view, right? And I'm also visible on the YouTube. Let's do it this way. Okay. All right. So here's a very lonely user. Not a lot of interaction happening now. Here's a system, maybe a search engine or a conversational agent or a recommender. Still a few bits and pieces missing, namely the context. Right, as Norbert and Nicola repeatedly explained yesterday, the context matters, tasks matter, background knowledge matters, time of the day matters, location matters. A lot of stuff can matter here. That's all packaged in this frame of the context. And so the core question that is behind the hour and a half that Romain and I will be entertaining you is, how can a search engine or recommender system or a conversational assistant get better through these interactions? So not just offer results, but also learn from what users do with those results, given the user, given the context in which this user operates. And so here are three key concepts. So the context, that could be the user history, user query, a profile, time of the day. Policy, that's a mapping that, given a context, selects an action. And the action could be an answer, a song to play, a result list, or complex Netflix-like multi-banner display. And rewards. Rewards that are returned. That was a nice reward. And it could be clicks or sounds or downloads or purchases, or could also be the amount of time that someone spends interacting with the results that are shown. So context, policy, reward. Now the policy, or the mapping that returns an action, could be deterministic. So given a context, this is the action. It could also be stochastic. So there's a conditional probability of an action given the context. And so the interaction, sorry, the policy interacts with the environment. It produces log data. And you can think of the log data as a set of triples of context observed, of actions selected, and of rewards observed. Right, so if I log on to a search engine anonymously, then the context is at least the time of the day and my query. The action is what the search engine result page probably. And the observed reward is maybe a click on the item at rank 3. So some examples: ad hoc search, not personalized, what I just mentioned. Context query, the action, rank list of documents, rewards, clicks, dwell time. Other example, product search, personalized. So then the context would be a query, user profile, my past interactions. The action would be for the system to show a grid of items. And the reward could be clicks, purchases, conversion. Ad placement. Context could be the user profile, but maybe also the page that I'm about to visit, where the ads are going to be placed. So profile, maybe a bit more context. Action is this slate, this complex combination of ads, and the rewards again is clicks and conversion. One more example, in a conversational recommendation setting, again, the context, the user history, so maybe past interaction that I have had with the system, the current ongoing conversation. The action could be an item recommended to me. Here's a song you should listen to. That's the book you should buy. And the reward could be the task is completed, namely of me finding a song I want to listen to, or booking a ticket for a plane and conversion. Now, there are two core problems. One is learning a policy. So finding a new policy that's better than the current policy, so that we can bring even better results to users, and evaluating the policy. So understanding how good we're doing. And often this could be done online while you're executing this policy, trying to find out whether you're doing a good job or whether you're making mistakes and should try to do an even better job. Now, in thinking about both problems, learning of policies and evaluation of policies, it's important to keep a few distinctions in your head. So what is online versus offline? So you're probably all familiar with this, but let's recall it anyway. So in general, a method that receives input sequentially operates online, and so that typically involves a bunch of tasks with a sequence of actions. Like when queries stream in, and the system has to do something in response to each of those queries. The other is offline processing or batch. They don't really need direct human interaction, and typically learning in batch or offline mode would be you initialize your weights, and then you go through your data, update your weights according to your learning algorithm, and you might repeat that a bunch of times. And so in IR, a typical offline computation would be doing anything that doesn't directly depend on the query. For instance, scrolling the website, normalizing the content. And the typical online computation would be stuff that does directly depend on the user, on the query. So that's one distinction, online versus offline. The other important distinction is on policy versus off policy. Now, in on policy learning or on policy evaluation, what we try to do is evaluate, so assess the quality, and try to improve the same policy that we're actually running. We're rebuilding the ship as we're sailing it. And with this metaphor, you immediately get the risk of this. When you rebuild the ship while you're sailing it, things might go wrong. Off policy is you evaluate and improve a policy that's different from the policy that was used for action selection. So often the terms that you will see being used in this context is behavior policy or the logging policy. So the logging policy is the policy that was used to collect the data. The target policy is the policy that we're trying to learn, the better policy. And so the interesting thing here, of course, is you're trying to come up with new actions that the old logging policy may never have taken. And so the more crazy, the more innovative your new actions are, the more uncertain you will be about their potential impact based on the historical log data, because the old logging policy never took that action. Right? So the more this is innovative, the bigger the uncertainty. Now, online policy evaluation can be done in a number of ways. We'll mention two of them, A/B testing and interleaving. So what do we do in online evaluation? We have two policies, A and B. Think of them as two systems. We have our user population. One part of the user population gets the result from policy A. The other part of the user population gets the result from policy B. We collect all the log data. We usually run this for 2 weeks. And then we compute the average reward over this period. And then if we think that the reward for A is significantly higher than for B, then we go for A. Otherwise, if B is significantly higher than for A, then we'll go for B. So here, different users might get different treatments because they might be in the A bucket or they might be in the B bucket. With interleaving, something similar, but not quite. Here, everyone gets exactly the same treatment. What we do is, again, we have a policy A and a policy B. For a given context, so user comes in, submits a query. We ask the policy A what action it will take. We ask policy B what action it will take. We somehow merge these two actions. We also think about, okay, what if we're successful? Who's going to get the credit? Who's going to get the reward? Then we run that combined action. We see what happens. If there's a reward, and then we, according to our credit assignment, we give it to A or to B. We do that for a while, take the average, and then go with A or B. Which of these two, A/B testing or interleaving, do you think needs fewer interactions?
This one.
Why is that?
Because in the first one, so in A/B testing, we need a sample of data for both of these policies, separate samples of data. And this we need only one. Yes.
But also, that's an important part of it. Another important part of it is for A/B testing, we're looking at two user populations and averaging over these populations. Here we're looking at a per individual user comparison. And it turns out that this will typically need 2 to 3 orders of magnitude fewer interactions than A/B testing. That doesn't mean that this is holy. There are quite a few issues with interleaving because this is a very simple interleaving method. So we have A and B. How do we combine those actions? Well, if we assume that we're in a retrieval setting, we have a ranked list here, ranked list there, we could do round robin. Flip a coin, okay, you first, you second. Flip a coin, who's next? And then go round and round and round until we've emptied out these two lists, put them together. User comes in, click somewhere. Where did this result come from? That one or that one? Right? So that's very simple combination method and very simple credit assignment. Now, what if we have additional constraints on these lists? For instance, we want these lists not just to be useful, so good stuff at the top, but also diverse, because maybe we're a news search platform, and we want to make sure that all the different channels of news all get enough attention. If we begin to mix these lists, we might actually mess up the diversity. By some accident, we might be very biased towards some channels and forget about all the other channels because they might end up wrong. So there are quite a few, even though you need less data here, which is a big plus, there are quite a few challenges that often come from additional constraints on the results. Some of them we can work with, some of them are harder.
Can I say that if I just do the regular A/B test, isn't then safer? Like in terms of you will have more, you need more interactions, but then your result will be with less constraints. Or
there's a sociological notion of safer here because people are a lot more used to A/B testing than interleaving. It's also easier, right? It's a direct competition, so it's easier to explain to people unlike us. However, it's not safer because you need to run it for longer to get the same amount of signal. So that makes it less safe.
So I was thinking in this case of the interleaving, and then yesterday we saw that there's like a lot of click bias, for instance. And maybe the person is picking the first position always, then you have to consider that as well.
Yeah. We'll get back to that, the click bias, different types of click bias in a few minutes. How am I doing time-wise? Thank you. Now, just to follow up on your question, actually. So why should we evaluate online, say with A/B testing or interleaving? Well, because we're directly looking at what users like, what they don't like. We directly see the impact of our actions. Right? And so we don't need label data of the sort that Noord and Nicola mentioned yesterday. Sometimes it's extremely expensive to collect. Sometimes it's not actually ethical to collect label data. For instance, in highly private search settings. No. For certain very small scale problems, you can't collect it. Also, the label data is stationary. Once you've collected it, those are the labels. Well, users are very non-stationary. Their preferences change. Even through the interactions with our systems, their notion of what's relevant and what's appropriate changes. For many users, once they've seen a result once, they don't want to see it again. Well, not in the same session at least, but maybe in the next session, because it sort of allows them to anchor back to where they were before. Also, there's a bunch of studies that show that the expert labels with Nicola's CIA experts don't necessarily align with real user preferences. Okay. So that would be positive reasons to evaluate online. Not evaluating online, why? Well, we're taking risks. We're trying out new actions because we need to learn. With new actions, we can make mistakes. We can give users a bad experience. Also, these online evaluations are complex to set up. So what if we evaluate off policy? So we have a running system already. It collects data. Now we're going to estimate the performance of a new policy using only the data that was collected. Once we're confident that what we've learned on that historical data is good enough, then we might try and put that online, maybe in an A/B test. Now, there's a bit of a word soup here if you go through the literature. Counterfactual evaluation, that's the same as offline A/B testing. So we have our historical data, we do the A/B testing on that historical data. That's the same as off-policy evaluation. of policy because it's not this new policy that new policy data that you're using for evaluation. Certainly counterfactual learning, unbiased learning to rank from historical data of policy learning. We'll see in the next couple of minutes lots of counterfactual questions. What if? Right? And, in a sense, what we're doing if we're trying to learn from of policy data is we haven't seen that action before, but what would happen if we had taken that action according to this data? All right, any questions at this point? We're going to be doing about 10-15 minutes of counterfactual learn to rank, and then we'll go to Romain and the bandits. So here we're going to be asking this counterfactual question a few times. What would have been? What would have been the reward? What would have been the outcome? What should have been the winner, etc. Those types of questions. We'll come across the notion of importance sampling, learning from bias, and correcting for some of the bias in the log. So I think on Thursday, Ricardo will go give a talk on bias, right? It's probably not just this sort of bias, but also much more societal notions of bias and how they enter the picture and how you could correct for those. So our notion of bias is very much a bias as a consequence of the way in which we collect data. That's something we can correct for, or try to correct for. Now, just to drive home that point, we're shifting now for the next few slides from search to recommendation. We have these two users, Roma and Martin, and we've collected some historical data, both for Martin and for Roma. We want to recommend them the next movie. And so our movies are red, green, yellow, and blue. Some of this is observed with the solid circles. Some of it is not observed, the dashed circles. For instance, I did not watch the blue movie. So we don't know what I think of the blue movie. I never saw it. And Romain did watch the yellow movie, but he didn't rate it. He didn't say this or that, or not even flat, nothing. There's no no judgment from him. So we have this problem of missing not at random. Missing not at random for different reasons. There's a popularity bias, so more popular items are rated more often because they're people are exposed to them more often. There's positivity bias. If something is shown high in a ranked list, people are more likely to click on it, inspect it, because it's in their face. That's one thing. The other, that's actually rather position bias rather than a positivity bias. Positivity biases users are more likely to rate the items that they've liked. They typically rate the items that they liked a lot, and the items that they hated, really hated. And the ones in the middle, they often don't bother to share a rating for those. Now, we need a bit of notation for the next few slides, so I hope it's not too much. We have users and states, state of the user. We have documents, movies, a slate, so that's a complex combination of items, a result page, for instance, or a product grid on a product search site. And we have actions. We have observed rewards and estimated rewards, a data set, a policy. We have an event, an examination event that we'll see in a bit. We have expected values, and then we have some distributions, uniform, normal, and Bernoulli. Okay, so users, documents, rewards, and then expected value, those are the ones that you'll see most. So we have data because we have a running system, the logging policy. And now we want to learn from this. We want to use this data to evaluate. An important concept here is importance sampling. So we want to estimate a certain quantity, a mean, variance of one distribution by sampling from another. We would like to estimate the expected reward for a user given a movie, but we've only observed these biased instances. The biased instances being what's in the logs, what the logging policy decided to show, what the users decided to rate. And the counterfactual question to ask here is, what would have been the average ratings under a uniform distribution? That's what we're interested in. Now here, so what important sampling tries to address is in the data, what was the probability of observing this data point, user and movie. And so what you see here is let's see, the observed rating. So we're on a 5-point rating scale from 1 through to 5. We see this positivity bias, right? Movies that people like a lot, they'll really give ratings for. Movies that they really hate, they'll also give ratings for, but very negative. The ones in the middle, again, look at the blue ones. The ones in the middle, not too many people bother about sharing their ratings. What we try to do then is to correct for some of this. And then so what seems to emerge here is something that looks a bit more normal. So the average rating, and some are really great and some are really poor. Now, we can do this. We can do this by taking into account the probability of actually observing an instance. That means if we see an instance really, really often, so we're facing these popular items, then we should not give them too much weight. We should actually reduce their weight. And if we see a few items rarely, we should maybe increase their importance a little bit to account for the fact that we didn't see them a lot. But they still have to make be part of our estimates. And so that's what happens with this counterfactual estimator. We look at the observed rewards. We then correct by the propensity, by the probability of observing these items. We do this across all of our user item pairs. We normalize, and then this is unbiased because we corrected for the probability of observing these items. Now, this is unbiased, but it could have really high variance, because what if there's an item that's super rare that we've only seen once or twice, and others we've seen thousands or even millions of times. In for these super rare instances, this value will be extremely high. Sorry, this will be really small, so we divide by it, and so this really blows up. But the variance is quite substantial with these counterfactual estimators. There are a few tricks to correct for this. In the tutorial by Saito and Joachim's, you'll see a whole range of ways of dealing with this. One is simply clipping the propensities, normalizing them. There are quite a few ways of dealing with this. Now, what we'd like to do is learn from logs. And so here we have a search engine result page for the query Lisbon. We see a few items, Wikipedia page, touristic pages, knowledge panel on the right, some questions here in the middle. And then if we look behind the screen, we might be seeing something like this. I hope this is not readable. This is a dump from a log that was shared a while ago. And so what would typically be in this log is the user ID, the query, a timestamp, the rank of the item that was clicked, and the ID of the item. Now, the more useful log would not just have this, but also record what other things were shown at the same time as the item that was clicked. Right, because then you also have you don't just have an absolute reward, you also have, in a sense, a relative idea of which items were preferred over which other items. Now, there can be, as we discussed a few minutes ago already, can be lots of biases in the log data. Position bias, users are more likely to see an item at the top of a page, to see and interact with it. Item selection bias, our catalog, our index may have millions of items. We can't show all of them. We can only show a few dozen if we're lucky, and sometimes even less than that, if say we're on a small screen. So there's an item selection bias. There are, if we don't return certain items, then users can't observe them. We cannot see any rewards. Trust, users may trust the search engine to return relevant results and are therefore more likely to click on them. And there's more. Now, this idea of importance sampling, so reweighing some of our observations. Becomes particularly interesting when we look not at individual items, but at slates. So combinations of multiple items. In grocery shopping could be a basket, on Spotify it could be a playlist, on the search engine it could be the SERP. And so in a movie setting it could be a carousel of multiple movies. That's the action, we produce a slate. The logging policy is this pi of L here, the probability of producing a slate for a given user. And under this logging policy, what was the probability that the slate was returned? Right, remember, we have a logging policy and we have another policy. Right, Roman? Now that we're talking, Roman, why is this too small? This quantity here, the probability of a slate given a user.
It's very unlikely that you see exact combination of items on the page. So that probability is going to be very small because you can have a lot of items associated with billions. And so if you even consider all the possible combinations, the probability of seeing one event is very small. That's why if you want something like this doesn't report wherever it's.
Okay. Now, what if we try to reduce the space a little bit by aggregating, for instance, not we're, at the end of the day, we're interested in good items and forming slates with good items and showing those. And so what if we try to focus a little bit more on the items in the slate? So what was shown at which position? So something like this, right? So the probability that a system chooses, the probability that that we're showing at position J, this item Yj. Why is that better?
Well, it's better because now you don't have to consider all the possible combinations of items in the space, but just the fact that when item appeared, actually certain wrong. So this will typically be a little bit bigger and so less variance related risk. But yeah, that's still really small, but I didn't like it.
Now, what if we adopt a somewhat richer perspective on this problem? One way in which this has been done in the literature is by looking at different user models, making some assumptions about how users interact with a result page, for instance. Two important notions there are examination and relevance, or examination and attractiveness. And so an alternative to the question that we just asked is, what, under the logging policy, what was the probability of the user examining the document? Why is that a better way of correcting than what we just did with the positions?
Because now we don't have to consider every time a very specific item appeared, but only every time a user observed a certain position, say, for example, and that happened basically. So that's this examination probability, for example, can depend just on the rank of the item, and it's really typically, something between 0 and 1, but close to 0. So we take less variance related risk, and we have more examples of such situations. So that estimator will have lower variance, and now it becomes usable in the web surf scenario.
And are you assuming that these observations are independent? Well, does that depend on the sort of user model that you adopt?
Of course, that really depends on the user model. So here you have an example of a position-based model, where the examination probability, like that the user examines a particular item, depends not only if it's wrong, but that's probably a simplistic assumption. So we have other models, and that's what comes in next example.
Okay. Now, we're going to do one more step, right? And so this is an estimator that is called the doubly robust estimator. And what does it do? Well, first, you try to get this biased estimate like we had before of a user's response, and then we apply a correction. But we apply the correction only on the difference with this estimate. Okay, so here's the difference with the estimate. And so why is this called doubly robust? Well, on the one hand, it tries to address the variance. On the other hand, it tries to address the bias. And so that's hopefully with this two-sided attack, you get a better estimator of the user response. Now, there's one question we've skipped so far, Omer. What's that question?
How to design the user model.
Exactly. How to get an understanding of, oh, what are these weights? Where do they come from? Any idea? Well, take a look at what people look at. I think we've seen images like this also yesterday, right? So when you do an eye tracking experiment, you can try to determine what a user typically looks at. And this F shape, right? an F shape is one that's been known for quite a while. Certainly here in Western societies, this is where people begin to look. This is what receives most attention. If you're interested in running eye tracking experiments yourself, you actually no longer need really expensive equipment. The price has come down a lot anyway, but you can run fairly sensible eye tracking experiments through a setup that you've been accustomed to for the last 2.5 years. A laptop with a camera. And it's very affordable. If you want to know more, talk to me in the break. Right. Next one. This is an interesting one. So we're trying to understand here, what is the likelihood of the probability that someone would look at an item just because of where that item is placed? Or why is a person looking at this item because of the quality of the item? And so some interesting different ways of trying to get these numbers, and that's by doing swaps. So suppose you have a top 10, and what you could do, it's an experiment. You will run risks, but if you only swap items in the top 10, for instance, your risk is, assuming that your top 10 on the whole is pretty okay, and if you swap items in the top 10, the risk is for damaging the user's utility is somewhat reduced. And so you can do pairwise swaps. You can only swap with the first item. If you're more adventurous, you can swap items from way below in the ranking into the top 10. Let's see whether they now trigger more engagement. And the last example is learning from logs, learning click models from logs. There are dozens or maybe probably even hundreds of those models. What's nice about them, one step back, increasingly now these are neural click models, but before the neural click models came along, they were all based on the probabilistic graphical models. So what was nice about that was you had to, as a designer of these models, you had to make explicit your assumptions about, for instance, examinations, attractiveness, satisfaction, and how these different variables were observed or not observed, and how they were dependent or not dependent on each other. And so one of the very first click models was user starts at the top, goes down, examines an item. If they find it attractive, they click and stop. So there's one result only. This is a later model where you can see that later items and examination depends on whether the previous item was examined, whether it was clicked, whether the user was satisfied or not. The parameters of these models can be learned by gradient descent or EM. And then finally, and then we hand over to Romain. With these click models, you can do two things. One is try to do click prediction. The other thing is you can do relevance estimation. So this concept of attractiveness can be used as a relevance estimator. And to assess a click model as a relevance estimator, we can use the metrics that Nicola presented yesterday. So, summary for this part. We have historical data. We'd like to learn from it, but it has different types of bias. We can correct for this with importance sampling. But that comes with high variance. So we need to make some assumptions about how users interact, and then use this to further improve our estimators. some of these weights that we need can be obtained either through eye tracking studies, these swap interventions, or through grid models. Sure.
So my question is so specific. Sectors is looking because there is previous parts that more than items or like because like if I want to design some support interfaces. So this might be helpful for me to see like how people like look and like where I can put my components like that. But like, are they looking for this is how they do or because there is like looks or like there is bias that I find the information I'm looking for. So like if there is searching where like all the time most different items are at the budget. And I know that. So they might be the first thing to look at it is the bottom because they have this bias that they love in this bit. So like how to use these models to help us like design some support interfaces and how to make sure or more understand how why people are looking. I don't know if you get what
Yes, you're absolutely right that for the past 2 or 3 decades, this is what we've all been exposed to. And it's very hard if you want to design new interfaces, new ways of presenting, to get people out of that mode. So you may actually have to first do some training before you can run a decent experiment. Having said that, there are lots of other aspects that play a role here. For instance, now this is a very boring result page, nothing visually stands out. But if we were to have, for instance, a banner here with videos, that would attract a lot of attention because we are very visual beings. And so then the attention distribution would be quite different. There would be a lot here because that's the position bias, but there was also the visual attractiveness of the video banner would sort of some of this here, and not just around it, not just the video banner itself, but also close to it, below it. And so if you want to encourage people to inspect more material further down the page, it helps to put some visually attractive things here. It's also something that you should be aware of when you're trying to, for instance, one notion that Ricardo might touch on is fairness of exposure. So whether we're in a two-sided market, we have users who want to consume stuff, but we also have suppliers who want to offer. So users could be news readers, so suppliers could be the news publishers or music lovers and artists, right? And we want every artist to get a decent opportunity. If they produce reasonable music, great. They should be shown. They should be. Now, how do you ensure that people will go a bit further down so that also these small artists, lesser known, maybe brand new, will get exposure? You need to do something to do that. If you put them at the top, that's probably very risky because they're unknown. If you put them all the way at the bottom, they're not going to get any exposure. So you need to play with this and try out different mechanisms, visual often, to achieve, well, the sort of thing that you described. Any more? Over to you, Roman.
Please, thank you, Martin. So until now, what we have seen is that we can put users inside the loop, inside the scheme, by learning from user data. But we cannot say it's fully interactive. because we are learning from logged interactions, but the system that was in place is different. So we are not directly interacting and collecting our own data. And that's what we will try to do right now. Okay, so we'll start with a very simple scenario and see if we can design some strategies to learn to interact with users. Then we will make it a little bit more complex, and we will see if the solutions can keep up with that added complexity. Then we want to take a look at the long-term effects of our recommendations on the user, because when we interact with the user, it goes both ways. And finally, we want to make a link with the first presentation, how to transfer all what we have learned from here to what we have seen in the first part and learning from that. All right, so the scenario is the same as before. So we have these, categories of movies that we'd like to recommend, but the task here is a little bit different. It's the example of a cold start scenario, where you have a completely new user who logs in to the platform for the first time, and they want to get some recommendations. So you have to, start interacting, see what they like, and maybe take the lead and propose some new things. And what makes it a hard problem is that, of course, every user will not like all the movies from one category. They have only a probability of liking it. And for example, Martin has a 0.5 probability of liking the movies. And you can see they like the first one and dislike the second one. So it means you have to try multiple times before you get a pretty good idea of what movie to recommend. Okay, some definitions. We have already talked about some of them. So these categories of movies will be actions inside an action set. The reward here is the user feedback, which is binary. It's either you like or you dislike, so 0 or 1. And we can define the regret. So the regret is the difference between the reward you would have gotten with the optimal action and the reward you have gotten with the one you have taken. So our goal is to make it to 0 because we want to find the optimal action. And actually, we don't just want to do it, in the end, after a billion interactions with a user, we want to do it as quickly as possible. So the objective is actually the cumulative regret, or expected cumulative regret, actually, because we will sum at each time step the regrets that we get. Let's try something simple just to get a better feel of the problem. So what we will do all the time is to keep an internal estimate of the value of each category of movie, and we will update that estimate when we get some information from the user. So on that diagram, you can see like an axis from completely dislike to completely like. And at first, we don't know anything about the user, so we just place our estimate, which is like this icon here. We just place it kind of randomly in the axis. But then when we get some feedback, we will move them up or down. And in dashed rectangles here, these are the true value of the blue and yellow. It means that for that particular user, the best action was to take yellow movies. So we'll start with a greedy strategy. So the idea is that we always take the most promising action, which is the one with the best expected reward. So at first, let's take a blue movie because we don't have any knowledge about the environment, and it's a like, so it goes up, as you can see. Now our greedy action, the most promising one, is the blue one. So we will take it, and this time it's a dislike, so it will go down. It's still our greedy action, so we continue up, down. And what you can see is that now we have only taken blue movies. So we have a pretty good idea of what they're worth, but we have never taken the yellow movies, and yet it was the optimal option. So we should have tried it at least once, just to get trapped taking always the same option. Now, a little bit more complex. We will take the greedy action most of the time, but sometimes we will take a random action, and this way we will have to try the yellow action at some point. So we go up. And now we will take a random action, and we just have two actions, so it's the other one. and we also like it. We'll repeat that a few times. And you can see that now we had to try the yellow action. So we were able to see that it is actually better than the green action. So this thought experiment here is to highlight the exploitation dilemma, which says that, on one hand, you want to minimize your regrets. So you want to take good actions. So you want to exploit the knowledge you already have. But on the other hand, you have to try different actions multiple times. So you have to explore. And so all the strategies that we're going to try and implement are about balancing the exploration and the exploitation. Okay, so here's a little bit of math for people like math. The metric we want to optimize is the cumulative regrets. We want to minimize it. So as I said before, that regret is always more than 0. It can be better than the optimal action. So it means that the cumulative regrets is increasing. And you might expect that after some time you find the optimal action. So your regret now becomes 0, and so that cumulative regret stops increasing. So you might expect that it converges. And actually, if you look at the regret as a function of t, you can see that it is at least proportional to the logarithm of t. So it does not converge. It has to go to infinity. So it's maybe a little bit surprising, but the intuition is that even if you try an action a million times, and a million times you get a like, you cannot be sure that it didn't just happen by chance. There is a very small probability that it did. Of course, it's very unlikely, but what this equation is saying is that probability outweighs the minimization of regret you get by gathering knowledge. So that's kind of a small defeat that we need to concede. But still, this is logarithmic, and the strategies that I showed you before, they are linear in the regret, because there is always a probability of taking a suboptimal action. So it means we have some progress to make. Inside the brackets, it's the constant that is behind the logarithm, which is also important if you want to study the convergence of it. And basically, if this constant is higher, it's a hard problem because you cannot get low regret, and if it's lower, it's an easier problem. I'm going to skip it for now, but I encourage you to go back to the slides and try to understand what makes a hard banded problem and what makes an easy banded problem. Okay, let's try a better strategy. So this one is based on the idea of optimism in the face of uncertainty. That means that it's a heuristic saying that when you are uncertain about something, you should try to reduce that uncertainty. And in our context, we have these actions, and we are pretty uncertain about their value. So we should try and reduce their uncertainty before exploiting. So what we're going to do is keep an estimate not only in the expected reward, but the full confidence bound. And now we're going to act greedily, not with respect to the expected reward, but to the upper confidence bound. So that way we are incentivized to take the actions with more uncertainty and to reduce that uncertainty. You can see when I take the blue action, for example, so it is shifted up, but the confidence interval is also made smaller because we reduce the uncertainty. And now the greedy action is with blue with respect to the upper confidence bound. Now it's yellow, etc. So that strategy is actually much better than the previous ones because it is logarithmic in the cumulative regrets. So it's not exactly the same constant as in the bound in the previous slide, but it's still quite good. Okay, now we will go to a natural idea after seeing that. We have a confidence interval, but why not actually keep in your system memory the full distribution of expected rewards. And to do that, we have to talk a little bit about Bayesian inference. I'm sure most of you are familiar with it, but let's just recall it. How can we maintain an estimate of the full distribution of rewards, and more importantly, how can we update it after we have interacted with the user. An easy answer to that is to use parameterized families of distribution. So you know some of them. For example, the family of Gaussian distributions, it has 2 parameters, and it means that you just need to store in your memory these 2 parameters, and that defines a unique Gaussian distribution. Now we have just defined a few concepts. The likelihood is our distribution of rewards for a certain parameter set. And the prior is what we think there should be. So it's our best guess about the parameters. And what we want to do by interaction is to update that prior into a posterior. And the way to do that is to use Bayes' law. You say that your posterior, so your updated guess about the parameter is proportional to the product of likelihood and prior. Okay, back to bandwidths. The algorithm of Thompson sampling is doing that, and it's based on a simple idea. You want to select some actions such that the probability of selecting an action is equal to the probability of it being optimal, considering your current knowledge. So the way we do this is by having these 3 steps. So first, for each of the actions, you will sample a set of parameters from your prior. Then you will select the action with the best expected reward according to this set of sample parameters. And then you observe the feedback from the user and you update it using Bayes' law. Okay, I guess it's a little bit abstract. So let's look at our movie recommendation scenario. So we said the rewards are binary, and this can be represented by a Bernoulli distribution, which has just 1 parameter, and it's the expected reward. Now, what prior and posterior should we choose? How do we design our best about that? And is to use a prior. It's so that when you do the update with Bayes' law, you stay within the same family of distribution. What changes is only parameters of the exact distribution. And it turns out that for this problem, what we use is a beta distribution, which has 2 parameters, alpha and beta. And so now, when you perform the update, you just change the parameters. So, for example, if it's a like, you will add 1 to alpha, in this simple update. And if it's a dislike, you'll add 1 to beta. So it's a very simple update, of course, very easy to compute. Once again, small animation. So you have the full distribution of rewards that you keep in your memory, and every time you will sample. So these are the dots here from that full distribution, and the action that you take is the sample that is highest. So here it's yellow, then blue, yellow, etc. What's really nice with that algorithm is that it achieves the optimal lower bound that I have shown a bit earlier. So basically, that's it. We have a solution for that problem. Of course, it depends on your use case. Maybe you care about the first steps, not the asymptotic behavior, but still, it's a very good solution. Do you have a question?
How do we set these prior? We set them like equal, or we check the history, or
that's actually well, you don't have any history, you don't know anything, so you have to be as non-informative as possible. And actually that's a very interesting question that you asked, because the prior that you take here is with alpha and beta 0 in this beta distribution, and you might expect that it's basically a uniform distribution, because that is between 0 and 1, it's probabilities. You might expect that it's just uniform between 0 and 1. And actually, it's not at all. It looks like a U. And the reason for that is that the influence of the feedback is not the same for a point which is in the middle and a point which is at the bounds of the 0-1 interval. So actually, what we call a non-informative prior, which is a bit of a debatable concept, in that case has to be, there cannot be a uniform distribution. Okay, so we have a pretty good solution. Now let's make the problem more complex and see whether we can hold it. So same scenario, but now we don't have like and dislike, we have a dwell time. So dwell time, it's an umbrella term which can mean watch time, listening time, reading time, and in the context of movie recommendation, it's watch time. So now we don't have binary rewards. Instead, we have some positive real numbers, and we can make the assumptions that they are normally distributed around some expected value. So we have a normal distribution with one parameter that we want to estimate, and a certain variance in the reward that we observe. And one way to see that parameter is to say that it's an exploration parameter. Because if this is close to 0, the values of rewards will be very concentrated around the mean. So you don't need a lot of trials in order to get a pretty good estimate of that mean. But if it's a very big parameter, it's very spread out, and so you need to try a lot of times. So that's one way to interpret it. Now we are going to do exactly the same. We are choosing a conjugate prior. In that case, it's also a normal distribution, which has 2 parameters. So the update is a little bit more complex than in the previous scenario, but still it's really easy to compute and really cheap. And yeah, actually, that is also a logarithmic lower bound. It's not necessarily the optimal one. It's actually still an open question. So if you want to solve that problem, you can do it. Okay, any questions on until now? Okay. Let's make the problem a little bit more complex. Now we will include some context. So context can be intrinsic, so that's your history on the platform, or it can be extrinsic. So for example, here Martin is consulting from his phone in the day in the Netherlands, and I'm doing it on my computer in the night in France. So we probably don't want to get the same recommendations. But otherwise, it looks pretty similar. But be careful, there is a huge difference, actually. Because now, yes, it's still called start, in the sense that we don't know anything about the particular user we consider when we start. But since we formalize that concept of intrinsic context, which is the history, what we are implicitly doing is that we want to leverage the knowledge we have from previous users, saying, a user with the same history is similar to the one we consider, so we might want to have similar recommendations. So it's actually more similar to the scenario that Martin showed in the beginning. Can we still use that Thompson sampling? The answer is yes. Now it's called linked yes, because we will assume that the expected reward depends linearly on the context features. So you have all of your context features, and you multiply by a vector, which is what we want to estimate, and that will give you the expected reward, for each action. So still the same thing, conjugate prior, it's also normal distribution. The updates now includes some matrix multiplication because we're working with multivariate distribution, but still it's possible to do it. Then you have some extensions to this algorithm. I'm not going to cover them now, but I encourage you to read that paper here and try for yourself some methods. It's really easy to implement, actually, so it's good to try. Okay, we are interacting with users. That's true, but it's very asymmetric because we only consider what we can learn from them, how their feedback can help us. But actually, they can get something from us. And it can be positive or negative. So here I will show you 2 examples. If you look at Martin's trajectory, you can see that he likes blue movies a lot. And our recommender system is really good, so it knows that. So it only recommends blue movies. So at first, he loves it, but after third or fourth or fifth blue movie, he starts to be bored. And you can see that now the new preferences of Martin are that he doesn't like blue movies anymore, or at least for a small period of time. And so that's an example of something bad that can happen if you don't consider the effect of your recommendations on the user. And this is just movie recommendations, so Martin gets bored. That's not great. But if it's maybe like political news or something, it's there are some studies that show that there can be some radicalization pathways because of such type of interactions. Now, if you look at my trajectory, you can see that initially I don't like the red movies, but at some point I get recommended one, and by chance I actually kind of like it. So now the recommender system will try again, and I have basically discovered that I like certain red movies, so I get interested in them. So that's like a positive effect, making you discover something new. So that's positive effects of taking long-term effects into account. So can we use bandits? Not really. It seems like the objectives are the same, because if we consider long-term effects, that means that when we take an action, it should optimize not just the reward here, but the sum of rewards. And we had the same objective before. We were minimizing the cumulative regret or maximizing cumulative rewards. That's the same. But the methods that we used, like the Thompson sampling, for example, they assume that your user is static. It doesn't change as a result of your recommendation, because otherwise, this update doesn't make sense anymore. And sorry, I thought it was on the previous one. And so what we need to do is to explicitly capture the change in the user's mind. And the appropriate framework to do that is reinforcement learning. It's not the only one, but it could be one. Some definitions, always the same. So you have some states. So these are all the possible states of the user's mind. You will take some actions. So, for example, recommending a movie. You will get some feedback. Can be click, real time, whatever you want. But what we add from before is the transition probabilities. And this is what describes how the user changes as a response to your recommendation. And of course, you also need an initial state distribution that describes the user when they arrive on the platform. So maybe you have guessed that this is hard to observe users' mind. We don't know what's in it most of the time. So instead, we must rely on proxies, which are observations. So it can be the history, it can be the extrinsic context, as we defined before. And that's why it's called a partially observable Markov decision process, and not just a Markov decision process. Now the goal is to maximize the cumulative rewards along a certain trajectory. So the trajectory will be the sequence of states and actions that you have observed. How much time do I have? Okay. Typically, you have two views of reinforcement learning. One is the policy-based view, and the other is the value-based view. So in policy-based, the most common paradigm is policy gradients. And the idea is that we will directly learn our policy to maximize our objective function. So that's J of a certain policy is exactly what we had in the previous slide. It's our goal of maximizing the cumulative rewards. And we want to do that by gradient descent. That means changing your parameter in the right direction so that it, by small steps, maximizes your objective function. And the key trick here is that theorem, the policy gradient theorem, which gives you an easy way to compute the gradients of that objective function. So now, it's still interactive, which means that we will have to alternate between data collection and policy evaluation and improvement. So we will alternate between collecting a trajectory with your current policy and improving the policy. And Martin said in the beginning that you have on policy, off policy. This is typically on policy because you connect with the same policy that you're currently using. Another view is dynamic programming. So this is value-based in the sense that you don't directly learn a policy to optimize your objective function, but instead you define a value function that tells you how good an action is, and you try to estimate the true value function of the environment. And the key trick here is Bellman's equation. So that's a way to decompose how good an action is on the long run into what's happening in the short term, so the reward that you get just after having interacted, and what's coming next. Many algorithms exist. Probably the most popular one is Q-learning, and it alternates between two steps. So you collect the experience and you improve the function. But now you don't have a real policy. So how do you collect experience? Actually, you will create an epsilon greedy policy with respect to your value estimate. So it's very close to the epsilon greedy strategy that we have seen in the beginning of that part. And yeah, there's also a critic which kind of combines both views, but I'm not going to get into the details. That is a very condensed introduction to reinforcement learning. There is a huge body of literature on this. That book, Sutton and Bartow, is always a place to start, so I recommend you read it if you want to learn more. Okay, so now we have a way to interact with users, to consider what we can learn from them, but also how we impact their behavior. But we have to do that online, so we have to collect experience, and that is not safe, as we have discussed earlier in the lecture. You can, especially maybe if it's a small scale recommendation system, you can afford that. But I mean, in a restricted scenario. But if it's a search engine, you're not going to just return random results to user for 1 billion times until you get a decent policy. So we might want to learn from that. So circling back to the beginning of the presentation. So that is the same screenshot as before. That's Query Lisbon. And here, the task we are going to consider has been introduced by Norbert yesterday, so it makes my job easier. It's the idea of optimizing the session. And you want to anticipate the need of users because you want that they find their information as quickly as possible. And actually, okay, you don't see, I guess you cannot read anything, but it seems like Google is doing something like this because when you type the query Lisbon, you have this people also ask snippets where you have, is Lisbon unsafe? Is Lisbon worth visiting, etc. So you kind of anticipate the needs of the user so that they have the information needs satisfied more quickly. So you have many ways of formulating that problem. Norbert talked about a few of them yesterday. But one way is to formulate it as a reinforcement learning problem where your reward would be something like, for example, every time the user has to enter a new query, you get a negative reward. So you want to minimize the number of queries needed to satisfy the information. Okay, this is some more intuition into why this is a hard problem. So we'll just skip that right now. You can find that after the session. Let's just naively try to use important sampling, like in the beginning of the session. So, always the same question, under the logging policy, what would have been the probability of observing? This time it's not just, observing an action, it's observing the full sequence of actions that led to it. Because we said that actions have a long-term effect on user behavior. So you have to consider the full sequence that led to it. And, we were saying that when that is too small, when the denominator is too small, we take risks of being sensitive to variance. But now we have a product of things that are small, so it's going to be even smaller. And so that's why no one uses important sampling in RL, because it's just too much variance and you never get a decent quality, never converges. Yes, that's just what I said. Yeah, an additional comment is that since you have to multiply the importance weights, the variance actually grows exponentially with the number of time steps that you consider. So that's really bad. And instead, what people are doing is called offline RL. And it's the idea that, you know, since there is too much variance, as soon as we are not like in the high density regions of the data, we should stay in the high density regions of the data. And so we want to find a way to create a policy that combines things that you see in the high density regions of the data. And mathematically, it's called staying within the support of the logging policy. Here are two ways of doing that. I see we don't have a lot of time, so very quick. So first thing is, in a value-based manner, you have your value function that tells you how good an action is, and you're going to select the best action according to the value function. But if there is like a part of the action space that you don't see, so the one right here, it's likely that it's going to be overestimated because of these variance risks. And so the one you're going to select is the best one, and it's in a place in a part of the data that you haven't seen, so you don't know how it's going to perform. And instead, we put some pessimism such that as soon as you are far away from the data, you know, it brings it down. So now the one you're going to select is actually inside the data, and you know what to expect. So you have less uncertainty about it. Another way of doing that is filtered behavior cloning. So here you completely reverse the problem. Instead of saying, okay, I have an action, how much it's worth? You say, okay, I am in a certain state. I want to get so much reward. What are the actions that I should generate to achieve that goal, that outcome? This is a very active area of research. We have new papers every day, so lots of things to read. So probably that these two things are not the things that we're going to use 1 year from now. Okay, just to finish, I want to go back to IR because in the last few slides I was in a more general RL community type of slides, and so we have some specific challenges in IR, notably the fact that the environment is highly stochastic. So if you have two users with the exact same history, they can react completely differently to the same recommendations. So you should never trust too much what you see in the data. Another thing is that there are a lot of actions. As we said, maybe on Netflix they maybe have a few thousand movies, but on a search engine they have billions of items over web pages, and if you consider the rankings, so the combinations, then it's numbers that you cannot even comprehend. It's so big. And last question, how can we integrate the user models that Martin has described earlier to these algorithms? Okay, I hope it was not too dense, but too quick to finish in time. But just a summary about what we have done. So first, we learned to interact with completely new users on the platform by balancing exploration and exploitation. So the appropriate framework is bandits or multi-bandits. Then we augmented these algorithms with some context features so that we can leverage the knowledge from other users and also some extrinsic context. And then we have tried to capture the effect of our recommendations on the user on the long term, and this is reinforcement learning. Some questions?
Yeah. Yes, and in this world of RL, can we assume that the user's behavior will change? Because you wrote somewhere that we assume that it does not change. But
that's a very good question, actually. So in the bandits, we assume that it does not change at all. In RL, it can change as a response to our recommendations, but it cannot change because of extrinsic things. Like if the world is changing, then it's still non-stationarity, and all the guarantees that we have don't work anymore. So the only thing we can say is that maybe it changes slowly enough, and that way we can adapt. But so yeah, you just consider the change as a result of the recommendation. Other questions? Okay, can you go to conclusion? I see it's already time for a break. Anyway, so this is what we have seen. So learning from user data and user interactions with counterfactual learning to rank, and then trying to interact with users directly. First in a symmetrical way where we learn from users, and then we also consider what we can bring to them. And we have a longer list of what we have not covered. Many things, in practice, it was very general, what we just said, because it doesn't explain what we do when we have very large action spaces, how we actually tune the hyperparameters when we learn offline. That's a really hard problem. Also, sometimes you don't have just one system in place that you learn from, but you have multiple policies. So what do you do in that case? Yeah, dealing with distributional shifts. That basically means that the world is usually not as you expect it to be, and sometimes it changes, as you mentioned. Also the fact that maybe we don't want to fully learn online or fully offline. We want something in the middle. Some interventions, but still mostly offline. And for example, we have that paper about it. We also didn't talk, of course, about the simulations and libraries. There exists a lot out there, but I think it's better to start by implementing yourself these methods. I mean, the bandit ones especially are really simple to implement, so it's really nice to understand what's happening. Last slide, and then we're done. So challenges. So accuracy also for rare phenomena, because we just consider the expected reward, so it's always mean, but actually sometimes you care about your long tail users, and we didn't do that in that session. You have also some efficiency questions, so how fast can you deliver the results? Reliability, when assumptions begin to fail. We mentioned user models, but what if we design the wrong one? What if we think we have a good user model, but actually it's not what's happening? Maybe it can cause some issues. Reproducibility, I think in every discipline it's always a concern. Resilience, it can be resilience against external factor. The world is not as you expect it to be, but also against adversarial attacks. It happens more and more. And also safety and privacy are typical challenges that need to be addressed. So, these are what we have shown are just like general ideas that can be applied to many problems in many scenarios. But there are really a lot of things to work on that are connected to it, and this is just a small list. Okay, I think we have final Q&A, and then you have a list of reference that you can find in this one. So any final questions?
Okay, so I have a question. So how are these RL based recommender systems or search engines or these tools in compare to like the standard models, like for example compared to collaborative ranking in recommender system?
Well, first, it's not really easy to compare them, because if you use the standard evaluation of collaborative filtering, for example, and use that with an RL recommender, well, does not mean the same thing, because in RL you care about the effect of your recommendation on the user, and so whenever you take an action, it should change what you see afterwards. So, for example, all the evaluation is based on next item recommendation, like I input hit rate or an ECG, etc. That is not something you can apply to RL because it's just one time step ahead. So actually, it's really hard to compare, and the only way to do it properly would be to have an A/B testing or interleaving. It's of course not cheap. Then, if you're asking about where we are right now in terms of research, I think there is like it's kind of new in the context of a recommendation, so probably that's there's still a long way to go.
And are they used somewhere in industry or?
Yes, actually. Well, it's I think the first one I can think of is in YouTube. Actually, they do some kind of RL. I think it's some like categories of videos in order to especially avoid the rich gets richer issue. But if you recommend to everyone certain videos, these are the ones that will be recommended to everyone else. So that's a problem in terms of fairness with respect to the content creators. There are actually some people who use RL in maybe more restricted scenario, like you have a system and it has some parameters, so you can actually tune the parameters using reinforcement learning. So that's also something people do.
Okay.
I don't know if I missed that part, but what's the impact, let's say, because we have the logging policy, right? And that was the system that we have in production that we can logs. What if you have a very bad system? And then how can you build on top of that?
Okay, actually, bad is probably not the worst scenario. Worst scenario is something narrow, because for example, extreme case, whatever the user is, you always recommend exactly the same list. You cannot learn anything from that. It's completely ambiguous, and you are never going to, you just have one list to recommend, and since you cannot invent what's outside of the data, you have to recommend the same list. So no improvement is possible. Now, if you have a completely random logging policy, that's actually the best possible case because you cover all the data. There is no bias, so you can just combine it however you want. In practice, it would be somewhere in the middle, and I would say in recommendation scenario and even more in search scenario, it will be very narrow, which is a big problem. And it suggests that we cannot have a big improvement at once. We have to take a small improvement, then deploy that new policy, take another small improvement, etc. So now you have a question of what improvement should I take? Because you have to improve your policy, you have to have a less narrow policy. So maybe you want to add some diversity for your data collection. No other questions? Okay, I think we can go grab a coffee then.
Okay, let's thank the speakers.
Thanks.